Okay. I'm just showing you how. So I'm just trying to explain how information travels around these networks in order to allow you to do inference. Okay. And so essentially we have this case where so the data inform the population. Sorry, the data inform the parameters that they derive from. Okay. And so each star tells you about its true apparent magnitude, each distance modulus tells you about the galaxy's distance, basically. And then on a per galaxy basis, these things also tell you something about the population level parameters. But because everything is kind of, information is free to flow all around this diagram, they also learn from all other galaxies about what the other galaxies think these parameters are, okay? And so you kind of naturally encode these statistical concepts like shrinkage and stuff like that, where because you're inferring something about the population, you will find that if you plot these on a scatter plot, they will be distributed more dispersely than the true apparent magnitudes, because the true apparent magnitudes know something about this from all of the other stars and all of the other galaxies that you've observed. And yeah, so Bly has some quite nice notes where he kind of codifies this actually in a mathematical form, but I think it's a bit too in depth for this. I think the one thing that I want people to get from this lecture is how to know what kind of inference algorithm you should use from one of these network diagrams. Okay, because I think that's a super useful thing to know. And so there are basically two things that these network diagrams allow you to do really simply. Okay, and the first thing is to it allows you to write down this joint posterior almost trivially. Okay, because the joint posterior, if you plug in all of these distributions, is just the product of every single thing that you've written down on this page. Okay, and so that is super useful because that's basically where you want to start from, okay? So what does the joint posterior look like in this case? Well, so you have what is this? So this is like the intercept of the period-luminosity relation. It's the absolute magnitude of a standard Cepheid. You have the slope, so the slope, which is essentially like d magnitude by the log period. And then you have the true distances to all of these galaxies and their true the true apparent magnitudes of all of the Cepheid variables. And so the joint posterior distribution looks like this, right? It's the probability of the absolute magnitude, the slope, the galaxy and star parameters for the observations. And so the first little cheeky tiny task is to write down what this thing is. Okay? So if you've got a pen and paper, I mean, it really is very simple. It's just the product of all of these terms on here, where you've got to remember that for anything inside this box, this big box here, you include the term n galaxy times, right? So it's a product of terms, and anything in this box, you've got to also do a product over j. Okay, so if you all could do that, then we can we'll use it later on for another one of these tasks. Okay, so does anyone need a pen, pencil, things? If anyone wants to write on the walls, there's things. I broke that.
Is it possible to zoom this slide a little bit?
To zoom it in.
I'm not sure if that happens.
So you can, if you go to, the slides are on, have you got Keynote on your machine? Because if you go to yeah, so they're on my GitHub thingy.
They're in the doc.
Yeah.
Okay, great.
Yeah.
Thank you.
Yeah, no problem. Okay. And so it's also worth noting that it's not giving you the full joint posterior. It's just giving you the terms that you actually care about. So it's giving you the terms that depend on the parameters of interest. Specifically, the only thing that you're missing out on here is the evidence. So you normally end up with a factor of 1 over the evidence, but you don't care about that if you're just doing parameter estimation. Yeah?
So when you draw the box for n galaxy there, why don't you need to include n star and s? I thought that's also different for.
Right, okay. Yeah, so in this very simple setup, I'm just assuming that there are n-star galaxies in n-star stars in each galaxy.
Yeah, but what I mean is for n galaxy. M star is the luminosity for
This one.
So that's the luminosity for stars.
This one?
Yeah.
Yeah.
Oh,
So
okay.
this, no, sorry, it's not M star as in.
Okay.
Yeah. No. The star is just a
Okay.
something. I could have put a C there. It's, yeah. So it's not. This is a stellar parameter.
Okay.
Okay. Anyone got any questions? Has anyone done it? John Burrell looks confused. We could do it together as well, don't worry. But so, essentially you just have one of these times one of these times n galaxy of these, right? Times n galaxy of those, times n galaxy, times n star of those and those. So I will get a pen and write what I think it should be in a couple of minutes. Does anybody want any more time? Let's do consistent. Okay. So essentially all this is just, so it's just the product of all of these things, okay? So you can just write it out as m star given, so you got all the priors, blah, what do I call it? And then you have a product over, so this is multiplying all of this, so you have a product over I, so all of the galaxies. And then each one of these you have a factor of this and this, okay? And then whatever you want for the measurement error. And then for each galaxy, you also have these n-star terms that have essentially the period luminosity relation. So that's m star s nu I at log p. And then some measurement. Something like that, okay? And so that is just a case of going through this diagram and multiplying all of these things together. But if you actually write out, from first principles what this should be, you'll get exactly this answer. And to replace the constant of proportionality, all you need to do is plug in, is basically say this is all divided by the evidence, which is probability of the mu hats and the m hats, okay? But you don't really care about that, so I'm not going to do that for now, okay? But so just having this network diagram is a really nice way of writing that down.
Can you explain the meaning of the terms?
Oh yeah, right. Of all of these terms, yeah. So this is the posterior that you want out at the end, right? So this is the probability of your model parameters given your observables, okay? And it's
given your m, like the probability of your parameters given.
Yeah, so this is the data.
Data.
Yeah, exactly. And so all this breaks down into is, so these are basically, so this is a prior on the absolute magnitude, prior on the slope, and then for each galaxy you have a prior on the distance modulus, and then a likelihood. for observing some distance estimate. Then for each star, you have essentially a prior, but that kind of terminology breaks down in a hierarchical model. It's kind of a prior on what the apparent magnitude should be given your period luminosity relation and your distance, and then your likelihood of observing those noisy data. And so the reason that's useful is because, I mean, if you want in the end just to know the parameters of your Cepheid period luminosity relation, then all you need to do is do a marginalization, right? You need to marginalize over the parameters that you don't care about, which might be the distances, the true distances, and the true apparent magnitudes. Okay? And we'll come back to that later. So it also allows you to do another thing, which is write down all the conditional distributions. Okay? So conditional distributions are, for example, what's the probability of getting this, some specific Mij, given everything else in your diagram, okay? Everything else in your model. This is really useful for doing something called Gibbs sampling, which we'll get to in the future. So the reason the network diagrams are useful for this is that basically this, so the conditional distribution for that depends only on something called the Markov Blanket, which is a really nice, completely opaque term. But the Markov Blanket is basically just the knowledge required that you need to predict that specific parameter and all of its children, okay? So you can basically say that the conditional distribution of this is only going to depend on the stuff that you need to predict it, so everything that goes into that box that it comes out of, and anything that directly descends from it. And so you can immediately say, for example, write down that the conditional distribution of this is going to depend on all of these parameters. So you can write, for example, this part down that you care about, and then you can actually then factorize that conditional distribution by basically taking only the distributions that come in and out of that node, okay? So if you wanted to write down the conditional distribution, all you need to do is say, well, it's the probability of this one that goes in and this one that comes out. And that's going to be super useful when we get to Gibbs sampling, okay? Right, okay. So in this specific instance, to kind of go through an example, it's a bit more involved than just writing that down. But so if we want to take try and calculate the conditional distribution for one of these nodes, like I say, you take the Markov blanket, so you take everything that you need to predict it and everything that it predicts directly, okay? Or you take these two distributions. And so you can write down that the probability for the probability of getting some value for this true apparent magnitude of the jth Cepheid in the ith galaxy depends on all of these parameters, but like I said, it just depends on the nodes going in and the nodes coming out. So the probability distributions going in and probability distributions going out. And so you can write it down as this thing here times this thing. And so if we assume that everything is normal, which is the thing that we were doing to simplify everything last time, then all that is the probability, so it's a normal distribution in the apparent magnitude where the kind of theoretical mean is this Cepheid period luminosity relation that we had before, okay? So it's essentially saying that the absolute magnitude of that Cepheid has some intercept and some slope that depends on the log period, and then you just add the distance to it to get an apparent magnitude, okay? So that's the kind of prior part of it, and then the likelihood part of it is just super simple, right? It's the normal in the observed apparent magnitude versus the true apparent magnitude with some measurement error. And because this is just a product of two normals, you can basically rearrange it and drop anything that doesn't explicitly depend on the parameter that you care about. And so you end up with it being a normal in Mij with some mean and variance that are given by this, which is your kind of like standard way of thinking about stuff. It's like an inverse variance weighted mean combination, okay? Like I say, we'll come back to this in a little bit to to actually use it.
So can I ask you?
Yeah.
This might be a little reductive, but does that mean that the probability of getting a given magnitude just means that it's proportional to drawing from a sample of a normal sample of magnitudes?
In this case,
Yeah.
yeah. So
Okay.
it's very, very simple because everything is because we've made the assumption that essentially everything in here is normal.
Mhm.
It's going to simplify
Right.
enormously. Okay.
If there were different distributions, then it would be a nightmare.
Exactly. Right. Exactly. Yeah.
Gotcha.
Could you explain why the bottom right sigma Mij goes into the, like, why is that a predictor of Mij? Maybe I'm not fully understanding the diagram. Like, why is that? Because
Right. It's just a right. Okay. So it's essentially a factor in this distribution. So it's really, so remember the small dot just means it's fixed.
it's fixed.
It's a fixed thing. So it's really, I mean, I put everything on here to be completely explicit, but really it's just a feature of this probability distribution because it's fixed. Okay? So it's not necessarily a parameter that it depends on, unless you, I mean, it would be if you didn't know it.
Fixed means it's like
If known. Yeah, exactly. So you can assume, exactly, you can assume that you've calibrated your instrument on some other star or something and you know its uncertainty.
But I guess I'm a little confused because it's not directly going into Mij, right?
For the conditional distribution, it's not, yes, it's not going, it would be if this wasn't here. So from last time, so if you, right, exactly. So if these, so okay, there's two different ways of drawing these network diagrams. You can include the probability distributions or not, but essentially, yeah, a better way of saying it is that if anything goes into one of these distributions that is directly connected to it, then you have to include it. So if these weren't on the diagram, this would go into that node.
Okay.
Yeah.
Thank you.
No, thank you for asking that. It's, yeah, that was confusingly worded. Right. Yes. So, okay. So those are two very specific things that you can do with network diagrams, but it doesn't necessarily help you in particular. But knowing the form of the joint distribution and or the conditional distribution allows you to choose what algorithm you need to use in order to actually do inference. Okay? And essentially there are three questions that you need to ask yourself. The first of which is what Mehmet was kind of mentioning, is the fact that, you know, can you actually do anything analytically? And so this little simplification here is showing you that in this case, you know, you've actually got a chance of doing that. The second question you need to ask is, can you sample from these conditionals easily, which, you know, in this case, you clearly can because it's just a normal. And then the third thing to say is, well, if you can't do anything analytically and you can't sample from these conditions easily, you know, can you actually break your model slightly such that either of those two things applies? Because if so, your life is going to be about 1,000 times easier. But so let's go through these, well, at least the first two of them in a bit more detail. So if everything is analytic, then, or if even parts of it are analytic, then you can do an enormous amount to kind of save effort, okay? And so this is why I set things up the way that I did, because if you assume that everything about that model is Gaussian, so Gaussian likelihoods, Gaussian intrinsic scatter around these things, Gaussian priors, then you can basically write everything down and simplify your model analytically really easily, okay? So imagine that we want to calculate, so this is the full joint posterior that I've written up here, this, well, that's the whole thing, but this is what we want to calculate. So this is the probability of the model parameters given your observed data, okay? Now imagine we don't care about the intrinsic magnitudes of these things, and so we want to marginalize over the stars, okay? We would want to do that because, recall, right, so this thing has dimensionality 1, 2, plus n galaxies times n stars. And so if you want to use MCMC, right, you learned a couple of weeks ago, you want to reduce your parameters, the number of your parameters as much as possible, because otherwise you end up buggered, basically. And so you can, if we can get rid of this, then we can get rid of n galaxy times n star parameters, and so maybe we can get to some kind of dimensionality that we can use a simple sampler on, okay? And so the cool thing about everything being normal is that we can do that, okay? And so, right, if we write down this, the posterior that we want, so the probability of the Cepheid period luminosity parameters and the galaxy distance moduli, it's just a marginalization integral. You'll remember what marginalization integrals look like, right? So you're going to have the thing that you want to marginalize over on the left of the divider, right? And then you can integrate over that to get rid of it. And so this thing here is just that I've written out on the board, which you can get trivially from this network diagram, right? And so you end up with something like this, but you want to do this integral over the magnitudes, the true magnitudes. And so you can basically plug that in and then shuffle this integral all the way down to the bit that depends on the magnitudes, okay? And so here we have just essentially something like the prior for these likelihoods. I'm missing a J. Times the likelihood, and you have it for every star in every galaxy. But if everything's normal, then right, you can just write this down as a product of two normals. And then we can do this step to basically rearrange this into a single normal that has this mean and this variance, where we basically shuffled all of the other terms into something that doesn't depend on the magnitudes, the true magnitudes at all, okay? Or in fact, sorry, other way around. Okay, let me see if I've drawn it here. Where have I written this out? I've written it somewhere. Not on this board, that's really annoying. So basically you can write down a normal as, sorry, a product of two normals as being, so normal with of some parameter with mean 1 and variance 1. Variance 2. So this is exactly equal to a normal with mean 1, like that. And then which way around? It's something like so this is just like completing the square and rearranging terms and stuff like that. It's exactly equal. So if you want to, what you end up with is one normal here that doesn't depend on the true parameter at all, and one that depends on it. And so if you end up integrating this over m, this thing just integrates to 1, right? And you get this prefactor out here that has the kind of the means of the two distributions in there, okay? And so you can, by rearranging it this way, you end up being able to just analytically marginalize over this, and you just get the prefactor out of it. And so you end up with this this form here. So the posterior that you care about, again, has these priors out the front, has a prior on the distances, the observed distances, and then you just have a product over a bunch of things that don't depend on the magnitudes at all. Okay? And so you basically got rid of the parameter dependence on those magnitudes, and so you've reduced the dimensionality by n galaxies by multiplied by n stars, which is an enormous reduction. And you could then plug this into an MCMC thing if you wanted to, but actually in this case you can just do the whole thing analytically. Okay, and that's because if you put an extra thing in there. If you write this all out, you just end up with like a ton of Gaussians, and you can rearrange the whole thing into this form here. Okay, so this is essentially the concept of generalized least squares, which I think did Hogg cover this ages ago. Yeah, so you can basically write it down as to use a bunch of different terminology. You have some response vector, which is all of these observables and things like that. a design matrix X, and then a parameter vector of stuff that you want to learn about. And so your parameter vector is the parameters of the Cepheid period luminosity relation, and in this case, all of the distances of all of the galaxies, or the distance moduli. This response vector has all of the fixed parameters of your model, so all of the kind of means and variances of the prior distributions and stuff like that, and then all of your observations in there. And then your design matrix basically has all of the relationships between these things. So you end up with stuff like you have the priors encoded in there and all of the Cepheid period luminosity relations for each one of the stars in your system. And so the fact that you could write it down like this means that you can essentially log this and take the derivative of it with respect to your parameters to get the maximum, so that's the maximum posterior solution. And you can also work out the essentially the covariance at that point, and just do it all analytically. So it's a really simple thing. In order to get your maximum posterior estimate of the parameters of interest, this is like plugging in a vector of observables, multiplying by the inverse covariance, and then this design matrix. And just doing this linear algebra is pretty simple. And again, you essentially this part of it gives you the parameter covariance. And so if you look at the Jupyter notebook that I put together, I can just show you on this. You don't need to run it on your machine. Where is it? So yeah, coding this up is annoyingly nitpicky, but it's just a kind of bookkeeping exercise. So there's an example I've put in there where I've coded up the design matrix that you have to put together, this vector of observables, and then the parameter vector as well. And so it's super simple. The actual solving this whole thing is just these few lines here. It's just that, basically. And you end up getting something out that looks like parameter constraints that look like this. So in this case, I have thrown away the distance moduli, but it's very simple in this case. Okay, somewhere, maybe. Where's my mouse? It's not there. Okay, so that's a kind of very special situation, okay, that only arises if everything is Gaussian. If you can't write everything down analytically, then you need to do something that's more intelligent, okay? And then the second question, so this is going back to this list of questions that we have, the next thing that you want to check is, can I write down all of my conditional distributions by looking at my network diagram and using the kind of trick of writing down all of the distributions that go into every parameter of interest. And if you can write down all of these conditional distributions and you can sample from them easily, then you can do something super cool, which is called Gibbs sampling, okay? So Gibbs sampling conceptually is very simple. All that Gibbs sampling is basically saying that in order to sample from the posterior of interest, you just have to loop through every single parameter and sample from its conditional distribution, okay? So imagine we have a very simple setup where we just have three parameters, theta 1, theta 2, theta 3, and some observations d. In order to do Gibbs sampling, ignore this for now, what you want to do is do this little loop here. So you want to essentially start from some starting point where you have a parameter value for each one of a value for each one of these parameters. And then you want to say, okay, for theta 1, I'm going to draw some new theta 1 from its conditional distribution. The conditional distribution is the probability of theta 1 given everything else in the model. So probability of theta 1 given theta 2, theta 3, and d. Okay? And then you just loop. Then you just kind of go over all of the variables of interest. So you take a sample from theta 2 to be the probability of theta 2 given. Now your kind of current state of the system is that you've updated theta 1. So this is the kind of iteration, the step, the sample number, or something like that. So you've updated theta 1, but you still have your old theta 3 and your data, okay? And so then you move on to the final parameter, sample this from the current state of the network, which is the updated theta 1, updated theta 2, and your data, okay? And then you basically just keep doing this over and over and over again, and you'll end up with samples from the posterior that you care about. Now, really, you should kind of randomize the order in order to do that, but you don't have to. It works.
You mean each n sample you should randomize over the like 1, 2, 3?
Yeah, exactly. Okay. So yeah, you should really go 1, 2, 3, and then 2, 1, 3, and then whatever. But I've never seen this break from not doing that. I have seen it break for many other reasons, but well, no, for one, me being bad at coding, but in very different settings. So what does this actually look like, right? So this is the best animation of Gibbs sampling I could find on the internet, which says something for the internet. So in this case, they're sampling some bivariate Gaussian, okay? And it's just going nuts. It will start again in a second. So what we're doing, so we just have two parameters in this case, right? X and Y that they're trying to estimate. But you can see each iteration of the sampler involves two steps, okay? And those are conditional. So in each case, you have everything else in your network is fixed, and you're just changing one parameter at a time. And so yeah, each iteration, once it goes back to the start again, basically involves a sample in. So probability of x given y, y given x, x given y given x, right? And so you have this characteristic way of stepping around your posterior that involves, essentially n parameter little steps that are all orthogonal to each other at the same at each point. I think the thing to note about this is that it takes a while to actually move across, this system, and that's because with Gibbs sampling you often have a very long correlation length between your samples. Just because of the way that it works. If this was completely not degenerate, then you would naturally move about rapidly, but it can take a long time to kind of creep up a very degenerate posterior doing this, which sounds a bit weird. Yeah?
Is there no way to sample both parameter updates at once?
So there are other algorithms that will do it at once.
Oh, okay.
Yeah. But with Gibbs sampling, it's just because of the fact that you basically have these little subsampling steps where you're doing conditional distributions. Okay. The reason why you do that is because the acceptance probability is 1 all the time, every time. And so even though you have this case where it can take a long, you have strong correlations between whatever, you have a large lag, you accept every single proposal. And so, you don't care about the dimensionality, you don't care about particularly curving degeneracies, although it can be challenging because, you're fundamentally making steps like that. And so to get around a corner, it can still take a while. But yeah, this is what I wanted to say was that even though it's a little bit involved to kind of code something up because you're not drawing, you have to work out every single conditional distribution and draw samples from it. The benefit is the fact that, you accept every single sample. And that's because, so you talked about Metropolis Hastings a couple of weeks ago, is that right? Yeah? So Gibbs sampling is basically a Metropolis Hastings algorithm with a very specific proposal where the proposal distribution is this conditional distribution. So your probability of getting some new theta 1 conditional on the old theta 2 and 3 in your data, okay? And so this is the way of writing essentially the proposal distribution. And so in Metropolis Hastings, what you do is you propose some new position and then you accept it with some probability A that is the minimum of 1 and essentially these two ratios here. So it's like the new posterior times the it's really ratios of these things. So it's the product of the ratio of the new posterior over the new proposal and divided by the old posterior and the old proposal. Okay, and so essentially, if you work out the maths here, basically this thing is always a conditional distribution. So these two terms are just conditionals, and then you can factorize this into a conditional distribution, and then basically these things cancel, and so that you always get, it's just a minimum of 1 and 1. So you always accept your proposals when you're doing Gibbs sampling. Okay, so this is the next task. So what I want you to do, and maybe it's worth just us going through this together. The original task was to write down the conditional PDF of this parameter here, okay? And so from this network diagram, what we know is that this thing here, the conditional distribution only depends on the incoming probabilities and the outgoing probabilities. So it's just the product of these two things here, okay? Except for the fact that this is actually wrapped up in an n star thing and an m galaxy thing, okay? So it might be worth, if we can get to the point where we can write down the non-simplified version of this, then I can show you how to simplify it in something that's really simple to calculate, okay? So is everyone comfortable doing that? Is anyone comfortable doing that? I can just do it and we can work through it together. Is that better or worse? Better? There's a nod. I don't want to blind you, sorry. I was going to be like, does anyone want to go doing it themselves, or do you want me to go through it?
Go ahead.
Okay. Okay. So, I'm going to get rid of this. Right.
You
So,
might need to move the board and frames.
oh yeah, can they not see it? Yeah, okay. They might have already gone. Is anyone still there online?
We're still here. It's kind of exciting when it's off screen. You know?
Sorry. Okay. Can you see that? Yeah. Now, helpfully, I left my notes upstairs, so we'll have to see if this comes out right. Right, okay, so what am I doing? Yeah, so we're writing down the probability of m star, yeah, given...
You might want to start off of where the projection is on. On the screen, it's hard to read.
I'll just write it lower down.
Yeah.
There we go.
I mean, if you move the board back where it was and just move the camera, pan the camera to the right, that might be the easiest thing.
That's so complicated. Let me get the black pen, and I'm going to write it low down. Okay. So I might skip out some terminology here, but basically, so yeah, let's bring it up here so everyone can see that, and everyone can see everything else, and everybody is happy except for me. Me's stuck behind it. Okay. So remember, we're talking about this Markov blanket here, right? So it's anything that's needed to predict it, which is just in this case, this stuff, and anything that descends from it, okay? And so I could write out all of the parameter dependence, but I'm just not gonna. And so it's the product of all the stuff that goes in. So this is essentially the prior. Sigma and star, and then all the stuff that comes out of it. So that involves a thingy over galaxies and over stars of all of these Cepheid period luminosity relations. Star S log P I J. Okay. Okay, so that's all the conditional distribution is. Okay, and so it's pretty simple to write that out from the network diagram. But then what do you actually want to do with it, right? Yeah?
What's the difference between the left-hand side of the proportionality sign and the
Yeah,
first
so
one?
that's why I should have written it out. So this is the probability of m star conditional on everything that kind of feeds into it. So it's of essentially it's of everything everything else in the entire network. Okay. Yeah. So this is of all other parameters and data.
When you're doing a Markov blanket, how many steps removed do you go when you go down the?
It should just be the children.
Just
so
the first
just
children.
the first children.
Okay.
Yeah, exactly. Yeah, or children.
Not grandchildren.
Not grandchildren.
Okay.
No. And so that's why you only need to care if you've got the distributions in there. You only need to care about the distributions going in and coming out. Okay.
So is it also just parents as opposed to
Well,
grandparents?
so it's not necessarily parents because it's anything that goes into that distribution. You see, so in this case, is there a
I guess
case where you
it's
can
still
see?
just like one removed in both directions.
It's not necessarily the case. Let me show you. The case that I put up there before. So it's not necessarily parents because there's something that's kind of,
I see what you mean.
You see what I mean? Yeah. It's basically anything you need to predict it and anything that it directly predicts. Is perhaps a better way of phrasing it. Was that where it was? Could be. Okay. Right. Yeah. Okay. So we've written down, assuming everyone can actually see this, what the come over here. Right. So this is the conditional distribution. These are all the terms that you need to care about. Okay. And in the end, the answer so what we're trying to say is there a simple way of sampling from this? So is there any way of rearranging this into something that we can just sample from in like one line with NumPy? Okay. Because at the moment it's not written out like that. And so in this case, we have everything being normal, right? So we have normal in m star with mean m bar star and variance sigma m star, okay? And then we have a bunch of these products of normals. Okay, so normal in Mij with mean mu I plus m star plus s log Pij and variance sigma int, okay? And so basically what we have to do here is we can just rearrange this to be a normal in m star, okay? Because if you write out like a Gaussian, right, this is something like e to the minus half Mij minus m star, which is exactly the same as squared m star minus Mij squared, right? And so we can just really swiftly just rearrange that like that. Mij. Okay, and then you can use a bunch of standard results for Gaussians to just rewrite this wherever I rubbed it off from down there into yeah, exactly, into a normal that kind of allows you to kind of go through all of these product terms, right? So this ends up being something like n. I wish I'd brought my notes. And then this is going to be an n in m star with mean. So if you, let's just write this as, so this is like the sum over I and j of all of these estimates of the mean. Oops. and variance sigma in. And this kind of makes sense, right? It's like if you have a bunch of estimates of what this should be that all have the same uncertainty on them, then the best estimate for this is just the mean of all of those estimates, and it has variance divided by the number of estimates that you have, okay? And so if all of these had different, whatever, if there was any reason why they would have a different intrinsic scatter, then you would just have the inverse variance weighted versions of these things. But so that is kind of combining all of those together, and then you just have to do a product of the two Gaussians, and that gives you the thing that you care about. And so what this ends up, if you say that this is like m twiddles, and this is sigma twiddles or something, like that, then yeah, you can you basically end up doing this thing down here, the product of two Gaussians. You end up with a term out the front that only depends on the two means, right? Which you don't care about for sampling because it doesn't depend on the parameter of interest. And then a term that has this in it. So let me just show you what it looks like. It looks something like m bar star m twiddles sigma squared plus sigma squared m twiddles. In fact, this is exactly true for this step, and that's exactly true for that step. Whatever, all this is exact. Times with the mean and variance. What's that? M bar, M twiddles, M bar. Right, so you end up, because you can write down this conditional distribution from the diagram and then write it all out in terms of Gaussians, you end up having a two-term thing here. This doesn't depend on m star at all, independent of m star. And so you don't need it when you're sampling, okay? And so you just end up with this being, in order to sample from this distribution, in order to draw a new m star, you just need to draw from a Gaussian, okay?
So you write proportional there, but when you do Gibbs sampling, do you need a true PDF?
No,
Normalized
so
PDF?
you only need the bit of that conditional that depends on the parameter that you're trying to sample. Everything else is a constant because you're holding it fixed for that specific subsample, or for that little sub-step of the iteration, okay? And so, yeah, when you're working this kind of stuff out, all you need to care about is any term that depends on the thing that you're trying to sample.
Okay.
And so in this specific setting, and in other similar settings, you get to the point where this is super simple, okay? And so in order to do a Gibbs sampler for this, all you have to do is draw from a Gaussian with that thingy. And so that was going to be the next task, was to code this up in the Jupyter notebook. So if you want to do this, does anyone want to do this? So if you have access to the Jupyter notebook, and you go to the here, I'll show you. This might be better so people can still. Whoop. So in the notebook, there is a Gibbs sampler that I've set up here. This is the thingy version of it. Let me drag this out. This is the incomplete version of it. So this is the code that you need to Gibbs sample something. So this is just setting things up. This is drawing some initial conditions for the sampler. And then for this to actually do the Gibbs sampling, you want to loop over the number of samples that you want. and then draw from the absolute magnitude, draw from the slope, draw from each apparent magnitude, and draw from the distance modulus. And so basically what you can do is you can kind of copy this structure and plug it into the absolute magnitude and just change the variable names and make sure that everything agrees with something like that, and that will give you a functioning Gibbs sampler. Does everyone feel confident enough to do that, or do you want to just run the full version and see it work? You want to see it work? Okay. So the full version, which you can also access on GitHub, right, let's just rebuild everything. So, where am I? So this is just simulating the data. Let's make sure that everything looks like it should do. So this is, what's this? This is showing the measurement uncertainty on some of these apparent magnitudes. You can also see that the apparent magnitudes are distributed with the right intrinsic scatter. I'll just go through the least squares crap, see what it looks like. Okay, so we've got a nice sample where everything is right in the middle. So this is the Gaussian least squares estimate of it. The Gibbs sampler is a little bit involved, but it's okay. Essentially, all I'm doing here is calculating. So to break it down, you end up with, you have to calculate this mean that you get from all of the Cepheid variables and their intrinsic scatter, intrinsic scatter, which is the first few lines, and then you plug in the prior information at the same time, and that allows you to draw just random normals with the appropriate standard deviation and mean. And then, yeah, like I said, for each step in the sampler, you draw the absolute magnitude, you draw the slope, you draw the apparent magnitudes and the distance, and it will run fairly quickly. So this should be doing, I can't remember how many samples, like 10,000 samples. Right, and it's done, okay? And so we want to test that this has sampled things properly, so let's just plot some samples from what am I doing here? So this is the absolute magnitude. And so the truth is just this blue line in here. These are the samples that the Gibbs sampler has put together for this quantity. And you can kind of see that it has, it's maybe not so easy from this plot, but it has actually got some quite long lag time scales in there, even though I'm doing, so I did actually 50,000 samples and then cut the first 25,000 of them. But yeah, if you then take all of those samples and plot the posterior distributions for the things that you care about, then it comes out right. Okay, and so this looks just like the equivalent plot for the Gaussian least squares estimate. Okay. So maybe it's worth, after the lecture, if you actually understand any of this, going back through and trying to put together this part of the sampler just to kind of, I think it's super helpful if you can do one step of this process all the way through. Yep.
Are there any surfaces that the Gibbs sampler can't explore because it has that one parameter update?
Yeah, right. So if it's, let me think. So if it's multimodal, I think it would probably struggle. Although I'm not necessarily sure, because if it depends. I've never actually tried to do a multimodal system with a Gibbs sampler. Because if as long as that ends up in the conditional, then you can do it. But then it depends whether or not that's hard to.
Because if it's like diagonal, and then it would just look along this line.
No, exactly. So it's certainly true that if you have a very long degeneracy like that, you can. And so people have set up Gibbs samplers for like CMB data analysis. The problem with that is that you end up. So you can end up in the situation where. Yeah, basically, even in the case where you have long degeneracies, you can do things like whitening the Gibbs sampler. So there are techniques where you can basically let it know about some estimate of the parameter covariance, which means that you kind of step a long way out and then map yourself back round, basically. So you can cope with degeneracies like that, but only if they're always there in your problem. And so, people have proposed this for the CMB, but they find out that it works in some settings and it doesn't work in other settings because of whether or not it's signal dominated or noise dominated. You kind of want to do different things at different times. So there are certainly some settings where Gibbs sampling won't work. The main one is just if writing the conditional distribution is hard to sample from, then you can't really do it. You can do something like Metropolis within Gibbs, basically. So if say, for example, you have 6 parameters that you care about and 5 of them you can write the conditional for, 1 of them you can't, then you can basically just embed a Metropolis Hastings step in there, and you won't suffer so badly because it's only one step that then doesn't have a bad acceptance rate. But if, for example, in our network diagram, it was like the apparent magnitudes of the stars, you couldn't use Gibbs sampling there because you have most of your parameters you can't actually sample from efficiently. Yeah.
So are you saying that the Gibbs sampling is more sensitive to multimodal than the Metropolis?
No, not more. It's the same. It just has the same issue.
This entire example was simplified because you assumed that the distribution of each variable was normal. Right? So how would it look if you assume that one of these variables is not normal and has a more complex distribution? So what would change in the code structure?
Yeah, exactly. So essentially, it's in like this step here, right? So if any one of these things wasn't normal, then it depends completely on what that distribution was. So in some of these cases, if you have something nice out here at the front, so for example, if you're varying the intrinsic scatter at the same time, and you put some kind of Jeffreys prior on that, or you have like a covariance matrix and you put a kind of inverse Wishart prior on, then you still end up with something that is analytic to sample from in the end. You just don't end up with everything being Gaussian. So you would still end up with a Gaussian in the kind of low-level parameters, but the higher-level stuff would be some other distribution, like an inverse gamma distribution.
You know it analytically, so that's
exactly. But so this is what I'm saying about kind of bending and breaking parts of your model, because if your true prior is something really hacky and minging, that means that you can't actually use Gibbs sampling, but actually a kind of, if you could say that it might be inverse Wishart distributed, and still, you might want to lose some fidelity from your model in order to make it tractable, in order to actually do inference in it in the first place. Yeah. Yeah?
So this is a bit more general, but I think everything that sort of you discussed over this in the previous lecture assumes that the model that you have is an adequate description of nature, right? So say it's me, and I think I have a good model, but it's not, because it has happened in the past.
Yeah.
But I run through this whole procedure.
Yeah.
Can you describe sort of what the outcome of running something like a hierarchical model on a flawed model, or a model that's a flawed description of nature, would look like when you then compare it to data? Does that question make sense?
Yeah, no, it totally does. It really depends on how bad your model is.
Right.
And so yeah. So I mean, the only thing you can do there is test it. And so what you can do is things like, so this is the posterior predictive distribution. If you you can make a prediction for what more data might look like given your model, and then you can observe those data and see what they look like compared to the predictions. And so you could do things like partition your data. It's a kind of machine learning approach, but if you take whatever, k-fold cross-validation, but Bayesian style, right? Hold 1/k of your data apart and predict it and see. But most people don't really do that. I mean, people do chi-square fits and things like that as goodness of fit tests, but the properly Bayesian way of doing it is to do this posterior predictive distribution. Yeah. So that's take most of your data, fit your model using it, use that fit to predict the remaining portion of your data and compare to the actual stuff that you had. And so you basically get a prediction for every data point that you haven't used. Yeah, exactly. Yeah. Yeah. Right. So there's one last thing that I wanted to cover, which is the case where you write down all of these conditional distributions, and maybe you can't get any further than this, right? Or you can plug in some actual distributions, but you can't end up sampling from the conditional. You can't end up rearranging it in a way that's actually helpful to sample from. And so in that case, what you might be able to do is something called Hamiltonian Monte-Carlo or hybrid Monte-Carlo. So has anyone heard of HMC? Yeah? Has anyone used it? Nope. No one used it. Okay. So this is one of these cool things where to make things easier, you make them harder. And so as well as sampling parameter space in Hamiltonian Monte-Carlo, you basically give your sampler a momentum as well. And you ask it to sample some momentum, okay? The reason for doing that is then you can write down the total energy of the system, so the Hamiltonian, right, as being some potential energy that depends on x. So x here is going to be your parameter vector, so this is like theta. And some kinetic energy that depends on the momentum that you've given the system, okay? And if you write down the dumbest thing that you can write down, you assume that the kinetic energy is half mv squared, right? You just end up with the kinetic energy being momentum squared over 2 times some mass, right? So this is a mass that you have to put into the system in some sense. You have to pick that in a sane way. And then some potential energy that depends on where the sampler is in parameter space, okay? Once you have that system, then you can use Hamilton's equations to just move around this parameter space, okay? So Hamilton's equations just tell you that the derivative of the position with respect to time is given by this momentum divided by the mass, okay? And the change in momentum over time is the derivative of the potential energy with respect to the parameters, with a cheeky little minus sign at the front, okay? And so what does that allow you to do? Right, okay, so everyone remember statistical mechanics? I last did statistical mechanics in 2003, which was a very, very long time ago. So statistical mechanics basically tells you that the probability of having a particle in some state with position x and momentum p is the exponent of a Hamiltonian with some factors in there that we don't really care about, okay? And so for this specific form of the Hamiltonian, with it being ux plus kp, right, you can just you can pull those two things apart, which is basically like saying the probability of it being x and p, of having this thing, it factorizes into a probability of it being in a specific position and having a specific momentum.
Do you need to implicitly assume that probability is Gaussian here, or no?
Which one?
The first equation you have there.
That's the canonical distribution or something.
Okay.
That's like pure statistical mechanics.
Okay.
Yeah. Yeah. Okay.
In the exponent, it looks like it's quadratic. So is it always Gaussian?
Ah, right. Okay. So sorry. So in so not necessarily for the position, but with that choice of the kinetic energy, then this is a Gaussian. Yeah, it's a Gaussian in momentum. Yeah, exactly. And so what we want to do, recall, for all of this stuff is we want to sample from the parameter x, okay? And so if we want this to be p of x, and we know that it's e to the minus u of x here, right? If we set u of x equal to minus log p of x, then that is just trivially true, okay? So what that is doing is that's identifying the potential energy of the system as the minus log posterior, okay? The negative logarithm of the parameter posterior, okay? And so in order to draw samples from the thing that you want, you can basically say, right, I'm going to set a ball rolling in a potential well where the potential well looks like the negative logarithm of the posterior that I want. And then you can just basically evolve Hamilton's equations and it will roll around in that potential well. And as long as you can do that accurately, then it will do that forever, okay? But the thing is, if you just if you keep the total energy to be the same, then it'll just roll around the same track over and over and over again. And so in order to get it to move around the rest of the system, you basically kick it. You give it a momentum shift, okay? So that's just sampling a new momentum, and then you allow it to evolve in using Hamilton's equations again. And then at the end of it, you can basically marginalize out the momenta by just forgetting them at every step, okay? So basically what you're doing is you drop it somewhere in parameter space, you give it a kick, and then you evolve it around the system with Hamilton's equations, and then you stop after a certain amount of time, and then you go, right, I'm going to kick it in this direction, and then it goes, right, okay? And it's super cool.
Kick that, how long do you have to evolve?
Yeah, right. So this is conceptually, it's very simple, right? Because you know the physics of the situation, but you have to set the evolution time. You have to set these this mass here, right, for the particle, and then there's all the details of how you actually evolve the system in how you do Hamilton's equations, basically. Yeah.
When you say introduce momentum, are you introducing like just a Gaussian?
Yeah, exactly. So, yeah, so for the assumption that the kinetic energy is the standard half mv squared, whatever p squared over 2m, the way that this distribution works is you have e to the minus half p squared, fundamentally. So it's a Gaussian distributed momentum vector. But because you end up marginalizing over these in the end, it kind of doesn't matter what you choose. It just so happens that that's super simple to work with. Yeah. Right, exactly. So cheating had the question of, yeah, you know, it's kind of conceptually fairly simple, but the details of actually doing Hamiltonian sampling is quite haggard, to be honest. Fundamentally, you know, in the ideal case, you would preserve your Hamiltonian precisely, and then that basically gives you a 100% acceptance rate. Okay, but you have to evolve this thing numerically, and so people, I'll just kind of skip through this because we don't have much time. So people end up using something called the Leapfrog algorithm that basically allows you to evolve this system in a way that it doesn't characteristically diverge away to infinity. It doesn't break. But because you're evolving the system numerically, you still end up having to do a little Metropolis accept reject step at the end, where the acceptance probability here is the minimum of 1, and the ratio of the exponentiated Hamiltonians at the end of the process and at the start of the process. If you have a very nice integrator that allows you to move around the system without much numerical noise, then these two things differ by a very small amount, and so this acceptance probability is still almost always 1, regardless of how many parameters you have in your parameter vector.
Sorry, quick question. Is that the Hamiltonian at the end of having done all the traveling before you kick it again, or is it just...
So it's kick, move, and then yeah, and then kick, move. And so yeah, so this is like a diagram of what this looks like. So this is, I'll go to the thing that I want to go to in a second. But yeah, this is just what you're saying there. So you start off here, you give it a kick in some direction, so it's moving in, so the log posterior here is a bivariate normal with equal standard deviation. So this is just what it looks like projected onto variable 1 and variable 2. You kick it around here and you evolve it for a certain number of steps. So each dot along here is one of these Leapfrog algorithm steps. You decide that you need to stop it somewhere, and you're saying, that's my parameter update. And so to do it again, you would just move it around. And so there's this super sweet little tool that this guy has come up with. It's got Hasselhoff on it, which is important. But so he has this really nice tool that that shows how various different samplers behave in different distributions. So this is kind of standard Metropolis Hastings doing its thing, where every green step is accepted and every red one is rejected. But so Hamiltonian Monte-Carlo is doing something like this. Okay, so every little gray thing is the momentum kick, and the blue and the green line is the final accepted new parameter sample. And so the cool thing about it, I don't know if it shows you here, is that if you have really awful posterior distributions, so this is a ring, right? and that has this weird distribution here. If you try and hit Metropolis Hastings with this, it just dies, right? Because it's got a symmetric proposal distribution, or you could give it this shape, but it would then break as soon as it got around here. Essentially, it's terrible at exploring this space. Almost every single proposal is rejected. But if you know something about the posterior distribution that you're going for, you see you can make these enormous steps around this distribution. And so it can handle horrifically degenerate systems, and it can handle very large distribution. Problems with huge numbers of parameters, because it's using your knowledge of physics to move around the system efficiently. Yeah.
So the only requirement to use Hamiltonian Monte-Carlo is you need your posterior to be differentiable, and then you can use it.
Yeah, exactly. So you need to be able to write it down in the first place, which is non-trivial in some settings, and yeah, then for it to be differentiable. So yeah, so that's the kind of vanilla way of doing things. Like Chi-Tung was saying, it's not that simple though, because you have to pick all of these parameters. So you have to pick this essentially like the mass for each parameter that you sample, and then you have to set up your Hamiltonian Monte-Carlo sampler. And so if you actually set up the step size poorly, or the number of steps poorly, so in this case, this is kicking in a certain direction and then evaluating for too long, depending on what posterior you're in, you just end up at the same spot, okay? And so there's significant amounts of tuning involved that has to be done on a kind of per case basis. And so what people have done is adapt HMC into something called a no U-turn sampler. So the no U-turn sampler, what it basically does is, so it's been given a kick in this direction, it evolves forward for a certain amount of time, and then it also evolves backwards for a certain amount of time to try and figure out the point where this trajectory turns around and would start going back to itself. And then, given that estimate of what the trajectory looks like, it then chooses something along this route, so that it basically never, it's trying to go as far as it possibly can without turning around, okay? And so there's a little link on this page to nuts, so you can see it going nuts. Yeah, that's the bad sampler. And so this is what nuts looks like. You can see it kind of goes forward and then it goes back. So I don't know, maybe you can see it. And then it just picks along these things. And so these things, you know, they're getting more and more complicated. There's more and more knobs that you can tweak in order to figure these things out. And so I don't do any of that. This is all coded up in a couple of different places. So the thing that I've used most in my career is Stan. So Stan has no U-turn sampling in there as a default thing. There's also PyMC3, which is both Python versions of this. So Stan has a number of different interfaces to it. So there's an R interface for the guy leaving the room.
Thousands of us.
Yeah, whatever. You were never new. So there's an R Stan, there's something else as well, but there's a nice Python interface. What Stan does is you have to write out your model in a specific language that it then translates into C++ and compiles for you so that it's super fast to run. And yeah, there are lots of other different options that you can do through Stan. So for example, once you've written your model, you can also get it to to simulate data for you and stuff like that. But it does all of the gradients that you need through autodiff. And most importantly, it does all of this tuning for you. So you don't have to set out a kind of mass matrix or things like that, or work out the optimal number of steps that you want to take in order to do your integration and the turnaround time or anything like that. It'll do all of this stuff for you. All you need to do is write out your model in a specific form. So the kind of minimal Stan model has a little data section in it where you are telling Stan what all of the observations you have are like, or all of the fixed parameters in your model, stuff like that. Then it has a parameters section, which is the stuff that you actually want to learn about, okay? So in this case, this is a Hubble constant estimate, so we want to learn about h0, we want to learn about distances to objects and their inclinations and stuff like that. You can ignore this section. The last little bit that it definitely needs is something that just sets out your model, okay? And the model is, it's written out in a slightly different way, or in a slightly confusing way, but all you're doing is setting out the potential that the sampler is going to be moving around in. So the negative log posterior. And so this is where this hierarchical model comes, or the network diagram really comes into its own, because you can write down the joint posterior trivially, like we did in the start of the lecture. It's just all of the product of all of the things of all of the distributions linking all of the parameters of interest. And so in this case, it's super simple, and the way that that Stan wants you to write it out is like a bunch of different sampling statements. So this is essentially a set of priors. So you say that the Hubble constant is drawn from some normal with this with this mean and width, ditto the peculiar velocity, stuff like that, and then all of your likelihoods. And so we've got like 2.5 minutes, but writing down the Stan version of this is very easy to do, and it's just a case of writing down all of these terms and then plugging them into Stan's syntax. So I've done that for you in the completed version of this code. This is if you want to try and do it yourself, it's not in the incomplete version. There's just a little model section to fill in. But for the case that we have, these are all the kind of observables and fixed things, the parameters that we want to estimate in the end. So this is the true distance for all the galaxies, the true apparent magnitudes for all of the stars in all of the galaxies. So Hamiltonian Monte-Carlo is so kind of efficient that you don't care about having all of these parameters in there. So I can't remember what the setup is for this case. There's 200 stars per galaxy, and maybe, I can't remember how many galaxies there are, maybe 2. So at least in this case, you have like 400 parameters here that you're trying to estimate, okay? Yeah, and then the true absolute magnitude and the true slope. And then, yeah, your model is super simple, right? Because everything is normal in this case, all of your priors just look like draws from normal distributions. All of your whatevers, so these are the things on the intermediate level that's not really priors, whatever. But again, they just look like normal distributions, and all of your data look like normal distributions too, okay? So have I got this to recompile? Right, okay, yeah, okay. So Stan will do this. Right, so it's sampling. It shouldn't take long. Maybe. We've only got how long?
Yeah.
We've got a minute. You can do it. You can't do it, Stan. I'm disappointed in you. Never run code live. I've got the answer on here already anyway. Oh, there we go, right, okay, done. So Stan will give you parameter constraints for all of these parameters, okay? So like 400 of these things. Whee! And hopefully it should come out looking like all of the other stuff, okay? Yeah, and so that was just sampling about 200 times as many parameters as the Gibbs sampler, and ends up giving you the same answer in the end, which is pretty cool. Yeah?
Does Hamiltonian MC have the same issue where it's bad in multimodal?
Yeah, absolutely. Yeah, exactly. So there are, Betancourt, one of the Stan authors, has big plans to make it usable in multimodal situations, but it's not in the current standard. way of doing things. And so in slightly multimodal situations, it's, you know, it'll run okay, but like if you have a massive number of parameters and they're all multimodal, it will, yeah, not good. And so if something is multimodal, so nested sampling should work for multimodal situations if you have enough live points that you're sampling at any given time. But again, that will start to struggle in very high dimensions. So if you have a really high dimensional, really multimodal problem, yeah, you're in trouble. Anyway, so that was the last thing that I wanted to say. And at the end of, so there's a whole bunch of other stuff that I got a lot of this from that might be useful. It's on the last slide in the slides. But so for a lot more kind of mathematical detail on a bunch of the things that I've covered, there's that. This introduction to Hamiltonian Monte-Carlo by Betancourt is really interesting. It's from a completely different perspective than what I've come from here, so you might find it more useful. And then this thing here is super useful. So this is the link to the to this tool for visualizing what different samplers look like, and I find it super useful for just figuring out what things are going on. So you can change the like posterior that it looks at. So you can make something multimodal and demonstrate that HMC will fail unless you have the kind of setup right. But yeah, you can change it from multimodal. Sorry, you can change the posterior that you're looking at, or you can look at different samplers. So this is nested sampling with lots of different live points, so it will actually shrink down to actually figure out this multimodal system. But I think this is really cool. There you go. I just figured it out. Hooray! Well done, nested sampling. But yeah, and it'll show you newbie algorithms like Metropolis Hastings failing at it at the same time. Anyway, yeah, that's all I wanted to say. Did anyone have any more questions, by the way? Yeah.
I have a question. I was wondering, in cognitive point, you can do dimensional analysis on the posterior to figure out if you wrote it down right.
Okay.
Do you remember what? So like if you have P of M.
Oh right. Oh yeah.
The dimensions okay. of M.
Yes.
Is like 1.
Right.
And on the other side, if you have it as a conditional.
Yeah. Right. Yeah. That's so because I think that when you have the proportionality stuff in there, that might mess that up because you're dropping terms that have other dependencies in there. But you can. Maybe that's true. Maybe that's not true. No, that's true because you have a constant of proportionality that presumably would be dimension full. Yes. So I'm not sure that check applies here, but you should ask Hog about that. Yeah. Yeah. Okay. Cool.